Okay, it's 1 minute past 6 here in the UK, so we will get started. Thank you everyone for coming once again to the Colloquium. This week, I'm very pleased to introduce Tobias Fritz, who's going to be talking on the law of large numbers in categorical probability. So Tobias, whenever you're ready.
Sorry, are we hearing Tobias?
I can't hear Tobias. No.
Sorry, yeah, I was still muted. Okay, yeah, thanks. So I assume that everyone can see my screen, can see the slides. If not, yeah, just interrupt again. Let me know. So yeah, it's great to be speaking here at the Topos Colloquium and Topos Institute. Looks like a really exciting thing to be taking off. So in my abstract, I had promised to talk about, various versions of the law of large numbers and formulations. But in preparing the talk, I kind of realized that this would be a little too much. So we've been working on this stuff and Markov categories and categorical probability for, well, more than 2 years now. And I realized having to introduce all the sort of background to be able to state the various reformulations would just take too much time and be too demanding for, I think, be too much material for people who haven't worked with this before. So I'll just limit it to one particular statement of the law of large numbers. But before I get to that, let me just get the sort of usual kind of, and I imagine many of you have seen a version of this slide already. Get this out of the way. So the particular approach to categorical probability that I'm going to present, there's a couple of precursors to it, I guess, and in particular Brandon's master thesis at Oxford. But the paper that really got it started, I guess, is this one on top here by Cho and Jacobs, where they really showed how one can do, the things in the title, Bayesian inversion in particular, talk about conditional independence, stuff like that. In terms of this categorical formalism. And then I wrote a long paper kind of doing some of the categorical aspects in some more detail and a lot of other things. And yeah, since then we're kind of redoing probability theory and statistics step by step in further papers. And so this is one particular approach to categorical probability, but for others, you also may want to take a look at, for all of those of you who are into this sort of thing, at the workshop Categorical Probability and Statistics that took place last year, and all the, thanks to COVID, I guess, all the talks are on YouTube. Okay, so now, today I want to really focus on the law of large numbers and the relevant prerequisites a little bit. And so I'll introduce just the relevant definitions from the categorical probability side. But also last year, I had already given more of a big picture talk on this at the, I guess it was still the MIT category seminar at the time. So you can also refer to that. But there's also then a talk tomorrow by Paolo at Cambridge. And as far as I understand, he'll also give a broader introduction than what I'm going to do today. So maybe Paolo can, I think he's here, so also just post a link in the chat to that talk tomorrow. Okay, so yeah, here's the law of large numbers really comes in many versions, even in the traditional and conventional probability theory. In some sense, well, there's a large number of large numbers, but this one is maybe the most common formulation. So, and I just wrote it down again here as a sort of motivation of what we're actually trying to get at. So if we have a sequence of real valued probabilities, real valued and independent random variables with identical distribution, and such that also, well, they have sort of bound at first moment, but that doesn't really, that's just a very technical condition. And then the point is that if you look at these averages, this is going to converge to the expectation value. And with probability 1, meaning, I mean, the xi's are random quantities. So also these averages will be random, but in the limit, they will become definite or deterministic and equal to that expectation value with probability 1. So the paradigmatic sort of example being that if you repeatedly toss a fair coin, and suppose that heads maybe corresponds to 0, tails corresponds to 1, then that way you can show that the relative frequency of heads will approach 1 with probability 1. And so it's a sort of self-consistency statement of probability theory in some sense. If you want to interpret probability as some kind of relative frequency at all, then it should better have this property that the relative frequency actually converges to this expected value. Yeah, so, but now this looks like a very analytical kind of statement. So where are the categories? And why am I giving this talk in this seminar? And yeah, before I get to introducing the relevant definitions, I can just now state a categorical version of the law of large numbers here. And so my goal is going to be to basically explain this statement. I'm not sure how much I should be saying about it at this point. Maybe you can just look at a string diagram and maybe try to guess what it could mean. But I'll get to all the individual pieces of it in due time. Okay, so but before I get to the technical definition, which are going to start in the next slide, I just want to say a little bit about the big picture. In that, what is this even all about? This categorical probability theory. It's in some sense, one can say, it behaves to probability theory, or it relates to ordinary probability theory in terms of probability measures, in the same way as kind of abstract algebra relates to studying concrete number systems, like the rational numbers and the real numbers. So abstract algebra just abstracts away from these particular structures and kind of tries to get at the essence of the algebraic laws and then kind of generalize things from there and build a general theory of such structures. And this is sort of also what categorical probability theory then tries to do, with ordinary measure theoretic probability as the special instance. An alternative kind of point of view is that traditional probability theory is kind of, in terms of this analytic synthetic distinction, analytic, it says what probabilities are and really gives concrete numerical values and calculation recipes for them and so on, while categorical probability is synthetic and it gives these higher level axioms that are more about how probabilities behave. So in particular in categorical probability, we don't really have numerical probabilities. And yeah, this is really all that I want to say, but if some of you are interested more in the motivations and why when we want to do this and what sort of scope one can expect of generality one could expect from this, then we can also talk more about this later. Okay, so here's a particular approach which somehow seems to be quite promising in that we've proven a number of these classical theorems, and now we can state the law of large numbers. So a Markov category is a symmetric monodic category equipped with a bunch of extra structure for every object. So every object X should come with a distinguished morphism from X to X tensor X, and also a distinguished morphism from X to the monodal unit I. So my string diagrams are to be read from bottom to top. And then, well, yeah, satisfying that this gives a commutative comonoid structure and interacting well with the monoidal structure, and such that the co-unit, so here, equation at the bottom here, the co-unit should be natural, but not necessarily the co-multiplication. And so the way to think about this is that the, well, co-multiplication amounts to copying information, and the co-unit corresponds to discarding information. And then these equations are sort of the obvious things that one would expect given this interpretation. And yeah, and in this way, Markov categories, you can say it should be quite obvious that they form something like a formal categorical theory of information flow. If you can copy information, pass it around, and then talk about, in terms of string diagrams, and talk about how it flows and how information processing systems compose. So in terms of the semantics, so there's many different and really interesting Markov categories. So there's some sort of landscape. And I don't really want to talk about this today because here the semantics for the law of large numbers we already have, at least roughly, the semantics should be measure theoretic probability. And so concretely, one can take the category where the objects are measurable spaces. And well, there are a lot of nasty measurable spaces. And so to get something nice, one restricts to standard Borel spaces. This is a kind of standard or, yeah, conventional, usual assumption. Many people also then talk about this in terms of polar spaces. So whenever you hear people talking about probability measures on polar spaces, it's the same thing. Yeah, one can show that these are all just finite sets or countably infinite or isomorphic to the unit interval. So they really aren't any more than these, which looks a little impoverished maybe. And then the morphisms are Markov kernels, which means that basically they're like functions, except that the output does not need to be a deterministic function of the input, but it allows so for randomness in the sense of something analogous to non-determinism. So the output is more like a probability distribution over the codomain, from which you can then draw particular samples which will be random. And the monoidal structure is a tensor product. So the usual Cartesian product of measurable spaces, which is the categorical product if you take measurable maps as the morphisms, but it's certainly not the categorical product in this category with respect to the Markov kernels. But it's still a monoidal structure. And the copy, the co-multiplication, and the co-unit are just the obvious things that correspond to this interpretation in terms of copying and discarding. And yeah, this is somehow a standard setting for measure theoretic probability. All right, and now I need to sort of fill this canvas of this particular flavor of category theory with some kind of additional mathematical definitions. So one thing is certainly that we may want to talk about when a particular morphism is deterministic, so when it does not contain any actual randomness. And so this is the definition here, that it's just deterministic means that basically satisfies the naturality for the co-multiplication. This is sort of how to interpret this equation in categorical terms. And what it means more operationally is that if you take the input to f and you feed it into two independent copies of f, and then suppose that f does something actually random, then at least for some of these inputs, then you will get different outputs, let's call them y1 and y2, that are at least sometimes different. But on the right-hand side, what we do here is that we apply the f to the input directly and then copy the output. So the outputs here are, by construction, will always satisfy y1 equal to y2. So whenever f does something actually random, then this equation will be violated, because on the left we can get distinct outputs. On the right, it's guaranteed that we always get the same output. But on the other hand, if f does not do anything random, then this equation somehow intuitively will be expected to be true. So this is how one can define the concept of determinism in a way which corresponds to the operational intuition that we have for what it should mean. Another way to say this is actually to note that, or to say that f should be independent of itself, but I'm not sure to what extent I should get into this. Okay, yeah, let me move on. So then, purely categorically, one can show that deterministic morphisms are closed under composition and are also closed under tensor product. That's just simple string diagram manipulations. And to give a concrete example, so yeah, and sorry, this subcategory then we denote it by C det. So just adding a subscript det to kind of indicate that these are deterministic morphisms. And for our intended semantics, Borel-Stock det, that one can show is the category of measurable functions between these standard Borel spaces. And so this is exactly as one would expect. Those Markov kernels that do not contain any randomness, those correspond to actual functions. Okay, so now if we go back to my version of the law of large numbers, you'll see that there are these mysterious triple dots here. And also in the conventional formula, the traditional formulation, we are dealing with these infinite sequences. And obviously this happens a lot in probability theory, that probability theory is in some sense all about asymptotics, things that apply to infinite, when you have infinite sequences. So somehow we need to be able to talk about this, and that's exactly what these dots here are about. And whoops. And so for that we need to be able to have a notion of infinite tensor products. And so yeah, now I want to introduce the definition of these. So suppose that we have a family, an arbitrary family or a sequence of objects. I'm just restricting now to sequences for simplicity, but we can do this for arbitrary families. And so then, since we have the co-units available, what we can do is that when we form finite tensor products of these objects, we get a lot of canonical morphisms, projection maps between these, by just applying the co-unit on some of the tensor factors. So when we do that, we get projection maps like this. Whenever f prime is a set of indices that contains the other set f, then we got a corresponding tensor product projection. And in probability theory terms, this basically corresponds to marginalization. In that, and we have a probability measure. A probability measure would be a morphism out of the monodal unit into our tensor product. So now this would correspond to a joint distribution of a bunch of, let's say random variables indexed by the set f prime, and then we can marginalize that distribution, which means we just forget some of these variables, and that way we land in the smaller tensor product. Okay, so this way we got at least the finite tensor products from our family of objects at least form some kind of big diagram. And the important thing to note is that it's a filtered diagram. And so we can take its limit, and so this is a filtered limit, and this is what we mean by the infinite tensor product, assuming that it exists. In addition, it turns out to be useful to postulate not just that it exists, but it's actually preserved by taking a further tensor by another object. And yeah, if we define infinite tensor products like this, what this amounts to semantically is basically, oh, don't I have this? Okay, so, no, it's in the next slide. Okay, so because of this, the definition in terms of the limit means that in order to map into an infinite tensor product, what we need to do is to just map into its finite subproducts in a consistent way. Then that would just be the universal property of this limit. Okay, we actually want something a little stronger, namely we also want to have that the limit projections are deterministic. And this is important because if we did not impose this, then on this infinite tensor product, we would not have fixed a particular comonoid structure. So because we're in this context where all these objects have come supplied with these comonoid structures, any sort of definition, any sort of universal property also should specify a corresponding comonoid structure in addition to a universal mapping property. And this is what the what a Kolmogorov products do here by imposing that not just the universal property, but also that the projection maps, which are the limit components, should be deterministic. Yeah, so from now on, I'm going to assume that you are in a Markov category which has these countable, which has Kolmogorov products, at least of countably many objects. And so this is satisfied in particular by our intended semantics and Borel stock. And well, in traditional probability theory, measure theoretic probability, this is a theorem that the universal property holds, and known as the Kolmogorov extension theorem.
Tobias, could I just ask a small question?
Yeah, please.
Do you have an example of a category that has a satisfies all of these except the fact that these projections are not deterministic?
Yes, I do. In that, so there are Markov categories where isomorphisms do not need to be deterministic. And so now you can take a Kolmogorov product, suppose it exists, and now take a non-deterministic isomorphism to another object. Then again, the universal property just remains, just transports to the new object, right? But because...
Yeah, that makes a lot of sense. Thank you.
Yeah, okay, yeah. I could also make it more concrete, but in particular, if you, well, I'm actually not sure if I can come up with a really concrete example off the top of my head, but this is the idea. All right, so another relevant now this is an axiom that a Markov category may or may not satisfy, namely that the category, call it positive, because this property has to do with the non-negativity of probability. That call the Markov category positive if whenever we have a composite of morphisms that happens to be deterministic, then this equation holds. And the way to think about this is that if you have a deterministic process, so this would be this one, this the composite sort of on the left, if you ignore the copying for the moment. And this thing, what happens here is a sort of copying an intermediate result of that process. Intermediate, if you think about it as a computation or something, it's an intermediate result. And now, since we copy that and it becomes an output, we also output that intermediate result. And then positivity says that whenever you do that, you might just as well compute the deterministic value directly and compute the intermediate result from a fresh computation, so to speak. So from a fresh copy of F. And so intuitively, it makes sense somehow that one would expect this to hold. And it's indeed true. In Borel stock in particular, it has to do with the non-negativity of probabilities. It's true generally, as we noticed recently, for Kleisli categories of strongly affine monads, in case that anyone has heard of this kind of thing. So there's also characterization in terms of monads. So now this in particular implies that every isomorphism is deterministic, which for my current purposes is actually why I want this. And it's not completely obvious, but it's also not difficult, just a kind of simple string diagram calculation. But not every Markov category is positive. In particular, if you allow negative probabilities, then this turns out to be violated. Okay, so now I need to get to another concept which has to do with the existence of this limit here. So in a traditional mesotheoretic setting, we just have a limit of some sequence of numbers, but a priori we don't know if this limit exists or doesn't exist. And it certainly doesn't exist in general. I mean, the law of large numbers itself says that it does exist with probability 1, meaning the probability that it does exist for a given random sequence xi is 1, but it doesn't mean that it always exists. So there's still a subset of measure 0 for which the limit does not exist, in which case the left-hand side is just not defined. And this kind of thing suggests that we should be, at a categorical level, we should be introducing or allowing some sort of partial morphisms. And this is what I'm going to now briefly introduce next. Namely, so there's this categorical framework for categories of partial maps, partial morphisms, given by restriction categories. And I'm going to be stating conditions for when a Markov category basically allows a nice calculus of partial morphisms by forming a monoidal restriction and resulting in a monoidal restriction category. And these conditions are, I guess this is pretty technical now, but maybe it's still a little interesting. Basically, we want to say that we take deterministic monomorphisms as those morphisms that specify our sub-objects with respect to which we can consider as the domains of partial morphisms. And in order for that to work well, I just need these deterministic morphisms to be closed under pull backs and tensor products. But then again, in the intended semantics, that is true. And in this case, these deterministic sub-objects actually correspond in some object X, correspond precisely to the measurable subsets of X. And this is actually far from trivial, that when you just, work this out concretely, what it amounts to, it's not so, it's not clear at all that these, that every deterministic sub-object would correspond to a measurable set. Because, as you may know, there's many different kinds of monomorphisms, and extremal, strong, and you get various kinds of sub-objects, and depending on the category that you're in, you get different notions of sub-object here. And here it's quite surprising that in Borel-Stock, these are precisely just the measurable subsets with the induced sigma algebra. And this is, yeah, somehow a very non-trivial fact. How's proof? I really don't know. But so using that, one can show that Borel-Stock indeed satisfies these partializability conditions. And so we can talk about partial morphisms, and that allows us to, kind of state, state the intended law of large numbers. Okay, so now going back to the categorical statement, we have quite a bunch of the ingredients. I've said what these copy maps do, and how they're defined. I've explained the triple dots. So this now just says consider the morphism into the infinite tensor product. So into the Kolmogorov product of some object X with itself. So this is sort of a Kolmogorov power. And this morphism would just be defined by, in terms of the universal mapping property, we just need to say how to map into finite subproducts. And while mapping into finite subproducts, we just do like this. If you ignore this for a moment, then this would be the map into X to the 3. And analogously, and so what I mean by the string diagram on the right with the dots is exactly this resulting morphism into the infinite tensor product. And similarly on the left. So now the only thing that I haven't explained yet is what is this resamp morphism. And so now I'll get to this. As the name suggests, this is about resampling. And so this is a term in statistics that generally refers to estimating the generalization error of your statistical model. So this refers to methods like cross-validation, that you just train your model on a subset of your data, and then you test it on a disjoint subset, and that way you can estimate how well does my model actually capture the patterns, the things that I'm interested in capturing, and how good will it be at predicting new data. So resampling is a general kind of set of methods similar to this cross-validation. So what I mean here, though, is something a little different, but it's closely related. So what I mean by resampling is basically that now you have, instead of just having a finite data set, now we have an infinite sequence. And what I mean by the resampling morphism is, so now here at the bottom, would be take an infinite sequence of elements from X and pick one of the elements of the sequence uniformly at random. So now, yeah, picking it uniformly at random doesn't really make sense because there is no uniform probability distributions on the natural numbers. So we can't really pick an element uniformly at random. But this can be made to work for at least a subset of all the sequences. And I'll write this down on the next slide and also show how it's related to forming the averages and the law of large numbers. But yeah, so when we do that, and this gives us, because it only works for some sequences, then we get a partial morphism from x to the n to x.
Sorry, I can't tell if this is a definition or a theorem. Is it a theorem about the existence of some morphism satisfying some conditions, or?
Yeah, it's neither. So far, it's neither. I'm just kind of trying to sketch what I want to get at, and on the next slide, it's going to be a definition of this morphism.
Thank you.
So yeah, and Borel-Stock, basically, I can say now I would want to define a morphism like this, which in some sense formalizes this intuitive idea of picking an element uniformly at random. And if we just have, let's say, yeah, and this means that in terms of as a Markov kernel, we would want it to look something like this. And now, as you can see on the right, this contains the sort of formation of the average from the law of large numbers. But the reason for why we would expect it maybe to be like this is because so the probability that an event S happens when we pick an element of the sequence randomly, well, that would just be the average of the individual probabilities given each of these elements given each element. And well, for each element, the event either happens or doesn't happen. So we get 0 or 1. And here we have this indicator function. And now if I want to sort of pick this element uniformly at random, I need to average all of these and take the limit. And yeah, if it wasn't an infinite sequence, but actually just a finite sequence, then this expression on the right, just without the limit, would indeed exactly now correspond to choosing an element uniformly at random. And now it makes perfect sense. We just pick each of them with probability 1 over n, and this is then that prefactor 1 over n. Okay, so this is the definition that we'd like to use. And it's partial. It's certainly at most a partial morphism, if it makes any sense at all, because the limit does not need to exist. So it only exists for certain sequences. But even then, the problem would be it doesn't quite work like this, because the problem is that a resulting map, when we vary S, the event S, we want to get a probability measure. But this is actually not necessarily a probability measure. It's not necessarily a sigma additive. So, but this turns out to be something one can fix by just tweaking it a little bit. But I just want to give, with these statements, just want to give a bit of a flavor of the technicalities that one has to deal with when defining this morphism. That there's quite a bunch of subtleties coming up.
Are these subtleties purely mathematical, or there's also something intuitive associated with this?
Yeah, that's good question. I'm not sure. I think as far as I can see, they're quite mathematical. But typically with this kind of thing, there is some intuition behind it, but I don't think I have a good intuition for what it is.
All right, thank you.
So yeah, we can impose uniform existence of these limits, at least for some S, and then it turns out to work. But Yeah. I can go into the details in case anyone wants to see them later. Okay, so now we have this morphism as a partial morphism, and now we really have all of the ingredients together. And now I can go back to the law of large numbers and explain what it actually says in this categorical formulation. So yeah, what it says is that if I take any sort of process, think of f as a process containing some randomness, and now we have infinitely many copies of f, and we all feed them the same input. And then what we do is that we just look at the output of all of them. We copy that output, and we sort of feed one of these copies outside. So these become outputs, but we also take another copy of each of them, and then we do this resampling thing. So then we get this infinite sequence of values, and we just pick one of them, and again, sort of only quote unquote, we pick one of them uniformly at random, very informally speaking. And now the statement of this equation, and now this is just basically a theorem in Borel-Stock in the sense of it being a reformulation of some version of the law of large numbers. The theorem says that this is actually the same as if you had just considered the infinite sequence. So the outputs here kind of match up like this, that this is x1, x1, x2, x2, and so on. So in some sense, this is saying that when you do this resampling from these infinitely many outputs of these independent copies of f, then what you get is just the same thing as if you had applied another independent copy of f. Now, formally, if you actually work this out, what this means at a level of the semantics, this is more like, I mean, I still don't have any real valued variables here, at least not directly, like in the usual law of large numbers. So this can't be can't be in any direct sense about real valued variables. So it's what it actually is about is more like it's the convergence of the empirical distribution. And so this is called the Glivenko-Cantelli theorem. It's in some sense quite a strong version of the law of large numbers. And that is really what is encoded in here.
Tobias, can you say what would be different if you didn't copy all those and you just exported one f on the right and you just did the resampling on the left? So you just had one output, what you call x1? What would be missing?
Let me try to draw this and see if I understand what you mean. Oh, oops. Sorry, I'm drawing somehow.
I think keep the same picture, but just dot off x2 through x infinity.
Okay. Yeah. Right. Or maybe I can just draw kind of over this, and so then there would be f here, right?
No. Keep the same picture you have there. Just dot off.
Oh, dot.
I think he's asking to marginalize over x2, x3, and so on, and just keep the first component.
Right. Oh, I see. Dot off in that sense.
Sorry. Yeah.
Okay. Got it. Yeah.
Yeah.
Right. Well, yeah. Then we got this equation, and so then these just drop out, right?
Yes.
So then we just get a single f on the right. And yeah, then this is this is nice. So then this is kind of saying that this resampling thing kind of takes you back to just a single f. You have these infinitely many copies.
It looks a bit like the classical law of large numbers. So yeah.
I think actually no, because, or I don't think so, because this is not about anything almost surely anymore, right?
So I see why the one you have here implies the one I said.
Yes.
And you're saying that the one I said is not quite enough to get the one you said.
Yes, right.
Interesting.
I'm
Let me make a
pretty sure
comment
about that. Yeah.
Intuition here. The version with all the x2, x3, and so on eliminated will follow from the classical strong law of large numbers. When you have the x2, x3, and so on included, then you're saying, in addition to the classical law of large numbers, that the original f's that you were averaging are in fact independent of that average. I think that's what having those parallel f's in the answer
Yes.
are. So it says the average goes to the expectation, but each individual one of the things you're averaging is independent of the average.
That's exactly right, and so in this sense, also this statement contains a little bit more information than just the law of large numbers. But if we do this marginalization, so if we do the dotting here, I don't think it's anything like the law of large numbers. It's a much weaker statement. In particular, there's no almost surely here. We're just sort of looking at what happens on average, or not looking at any particular sequence, but just sort of looking at the average sequence. And it would just be saying the law of large numbers holds on in expectation on both sides, which is quite a lot weaker, I would say.
Sorry, I'm confused on that last point. So I thought this weaker statement we were considering, on the left, you would have some kind of limit of the empirical CDFs. No. Isn't that kind of what that resampling thing is doing? It's
Yes.
Yeah. And so to me, like the Glivenko-Cantelli theorem says that like the empirical CDFs converge to the actual.
But it says that it does that almost surely. So it's sort of saying that for almost every sequence that you actually get as output of the f's, that convergence happens. And so that's why we need these. We need to do this. I mean, this is what then corresponds to almost sure equality. As yes, you obviously know.
I see. Okay.
So and if we did the marginalization, then it would still be a statement like that, but just with expectation on both sides. And in that sense, quite a bit weaker.
Okay. Thanks.
Okay, yeah, now we sort of seems like already in the questions, which is good, because this is roughly how much I had wanted to say. Yeah, I could just have this now made a little bit more concrete, maybe, or illustrate this a little more. Just now, I mean, already an interesting case is when f doesn't have any input. In case when f does have some input, it's basically the same thing as if f didn't have any input, just with an additional parameter. So having this additional input there is maybe not even that interesting. And so yeah, just can look at it for a fair coin. And so then, yeah, flipping infinitely many fair coins, and then picking a random one, kind of uniformly at random, again, very informally and incorrectly expressed, makes this latter one, which now corresponds to the first output, both independent of and identically distributed as the others. And finally, I want to try and make the connection to the strong law of large numbers, as I had presented it in the measure theoretic formulation at the beginning, a little more. and illustrate how it actually corresponds to that. Now, if we have our random outcomes, so now these would be the outputs here. Now let's call them C1 and C2 and so on. And now if we use the definition of the resampling morphism in terms of that limit, so then what we would get on the left, now I guess this is a little unfortunate because one can hardly distinguish the heads and the tails, but the one that's a little darker, let's say these, yeah, this is actually the head. These are the heads. So on the left, we would now have the probability, essentially the probability to get heads here, according to the definition of the resampling map. And so now the statement is that this is equal to, so on the one hand, this actually exists. So part of this equation is saying that when you compose these two, you get a partial morphism that is actually total. So the statement is that the limit exists on the one hand, and on the other hand is equal to just another fair coin, or what you would get, the probability to get heads from another fair coin. And so in that sense, this is the expectation here that we have in a traditional measure-theoretic formulation on the right-hand side. Okay, so yeah, this is basically what I had wanted to say.
But actually, this last equation, isn't this what happens when you ground everything on the right, or am I misinterpreting it?
No, this is still, the CIs are still random here. I'm not taking an expectation over the CIs, but I'm sort of conditioning on the CIs if you want.
Okay, thank you.
So let's say the last technical point I wanted to make is that we need to be, I should be a little bit careful in sort of claiming to have reformulations of the law of large numbers, because there's a lot of the difficulty in the proof of the strong law of large numbers comes in because of this assumption here, and in particular in the usual formulation, these variables are not necessarily bounded. So just a little bit of a caveat to say that what we get from this categorical formulation is a case where, well, now the xi's are basically these probabilities, and these can be pretty generic. And I mean, we can always translate on the real line and add, and so in that way we can make them basically to be equal to any bounded variable, any sort of bounded quantity, but we cannot make them unbounded. So in that sense, this categorical formulation is, at least in one respect, also a little weaker than the measure-theoretic one. All right, so yeah, let me end with a quick summary. So the whole point somehow is to get a kind of illustrate in a bit more detail some particular case study for which how that Markov categories provide a framework for doing at least parts of probability theory and statistics somehow synthetically in terms of more abstract axioms. And we don't really, at least as long as we stay purely at a synthetic level, which we can actually do for a lot of things, then we don't need to consider any measure theory anymore. And yeah, so in particular, we actually have completely abstract versions of some theorems of probability and statistics already. And so now I haven't been talking about these today, but I feel like I've already kind of talked a lot about these. So I didn't kind of want to be too repetitive. So two particular so-called 0-1 laws, which give criterion for when certain events or, well, when certain morphisms are deterministic. There's a version of the Fisher factorization theorem and sufficient statistics. And yeah, the most recent one is actually the Definite theorem, and maybe also the most interesting one so far that we've proven purely synthetically. This is a sort of, Paolo used a nice term, flagship theorem of probability. This is, I guess, the first one of that kind that we've developed purely synthetically. And yeah, I really would like to add the law of large numbers to this list of theorems. And yeah, so here's one particular formulation, but maybe I can say to end up with, I don't know how to prove it. It seems maybe quite doubtful that one can prove it completely synthetically, because already the very statement contains an additional structure in terms of this resampling morphism, and other formulations are similar, contain similar structure, which does not seem to be native to Markov categories in any sense. I have some ideas of maybe how to build it in, but it's, yeah, I think there's reason to be skeptical that one can really get this one too. Okay, and there's also some further hints of connections with ergodic theory, both coming from this. And so one can look at, further generalizations of lots of large numbers that people have proven for stochastic dynamical systems in ergodic theory. Also, the Definetti theorem sort of already goes in that direction, and would be nice to explore this particular connection further. Yeah, so and I think I should end with that. So,
can I ask a question?
So yeah, thanks a lot.
That was great. Thank you very much, Tobias. I guess, yeah, we've already started questions, but let's open the floor. Maybe more formally, if anyone wants to ask a specific question, then you can unmute yourself or you can raise your hand on Zoom or whatever. But if not, we can return to this kind of free discussion question method.
What hypotheses are necessary to prove these theorems? Do these work in arbitrary Markov categories?
No, none of them works in completely arbitrary Markov categories. The level of assumptions that we have kind of varies a little bit, but I can't really state the assumptions now because I haven't introduced all the relevant concepts, but we need these countable Kolmogorov products at least. We also need, for example, for the Definetti theorem, then we also need the existence of conditionals. That's then a categorical analog of, the formation of conditional probabilities. And we also basically need to have that a Markov category is actually a Kleisli category. So that it comes from a monad, we need to have a sort of probability monad underlying this. And these are the sort of typical assumptions that we make.
I have a question.
I was going to finish like a part 2 of my question. What about for the law of large numbers that you presented? Does this lend any natural ideas for generalizing in a different direction? Like, might this hold in categories of probability theory that work sort of like, I guess, when you go from classical to quantum probability, you relax certain conditions. And can you expect something like this to still hold in those cases?
I haven't thought about that yet. And in particular concerning semantics and other categories, I really have no idea. We'd have to think about how to define something like this resampling morphism in the first place. And so I don't know about this one. But the Definetti theorem, for example, which is also, a very recent result, there I kind of feel like maybe one can get the quantum case because, well, okay, no, sorry, I don't know about the representability, whether getting the Markov category as the classic category, which obviously doesn't work in the quantum case. But the other assumptions, I mean, yeah, Arthur has worked on conditionals in the quantum case. And I suppose also these Kolmogorov products will have a good chance to exist. So maybe one can make the quantum definite theorem work. But about this law of large numbers, I absolutely can't tell so far.
It looks to me like the quantum case will have much earlier difficulty, because in quantum mechanics you have the no cloning theorem, which says you can't just take the state of some system and produce two or more copies of it reliably. So sort of the very foundations here are going to need tweaking.
Absolutely, yes. But Arthur, I don't know if you want to comment on this yourself, but Arthur has solved this very elegantly by taking the by extending the morphisms a little bit, and basically taking the co-multiplication to be given by the dual of the multiplication of operators. And that way, in particular, it's non-commutative.
Yeah, so even though it's not interpreted as a copy map, even in some dual picture, you can still use that map as part of your structure in some ambient larger category. And then when you really want to see what results are physical, what are physical operations, then you can restrict to the subcategory of like suitably nice positive maps on your system. So you can still use that map. Yes, the no cloning theorem holds, but nevertheless, you can use that structure.
Okay, thank you.
Thank you.
I think maybe Evan was next. Yeah.
Yeah, I was going to ask something. So I like this construction of the infinite product as like this filtered limit, and it reminds me of how in probability it's common when you have like a distribution on an infinite dimensional space to have these statements that it's characterized by its finite distributions. And so I was wondering if you had thought about like whether the ideas that you have here could be used to work with like stochastic processes in this synthetic setting. Like you could replace the natural numbers with the real numbers and have some kind of process on the real line. Have you thought about that sort of thing?
A little bit, and that's definitely also something that I would really like to do. But then again, there's only so much time.
There also
And I feel like I personally unfortunately don't have a good background in stochastic processes, in particular in the continuous time case, which seems to be quite a bit more subtle than the discrete time case. And all these what was it called, various notions of equivalence of the stochastic processes already. So I'm not even sure if these Kolmogorov products would be the sort of correct thing to use in that context.
Okay.
Is the continuous time stochastic process still determined uniquely by its finite marginals?
I mean, I thought that there's statements like a Gaussian process, like it's determined by its finite dimensional distributions and stuff. There are kind of statements like that. So I am not an expert on stochastic processes, but it just triggered those thoughts in my mind, because there are similar sort of statements that I know show up there. So
then I guess all I can say is that I've been thinking pretty much the same thing, but haven't been able to. Yeah, we haven't been able to go further yet.
Yeah, and I have another unrelated question, if you don't mind. So so like the classical law of large numbers does have this condition that like the expectation needs to be finite.
Yeah.
And to me, it's not like just a technicality. Like if you take a Cauchy distribution and look at its sample means, well, they're all just Cauchy again, right? So like but it looks like your statement doesn't have this aspect in it. So like so if you take this statement, what do you have to do to sort of get something that looks like the classical law of large numbers?
So I don't know yet if we can get there all the way. But what this is so far is, as I've tried to sketch, corresponds in some sense to that classical statement in the case of bounded variables only.
Mhm.
So that's why there's no further kind of restriction like that, because it is already very restricted.
Yeah.
And that's because the probabilities that come out here, so the sort of things that we're summing up, are all in the unit interval only. But what we can do is to basically take a statement like this, and now suppose that our category is actually a classic category of a monad. And in that case, we can also prove, then we can say that this is basically a version of the law of large numbers for free algebras of that monad, because we're basically talking about convergence of distributions. So in some sense, this is about the law of large numbers, not on the real numbers as the traditional version, but on a space of probability measures, which is a free algebra of the monad. But now we can also do this for other algebras. And in fact, this version then will apply a form of the law of large numbers, which I know I haven't had time to explain, for all algebras of the monad. And depending on what monad one considers, it may be the case that this will lift that restriction to some extent, but I'm not sure.
Thanks. Yeah, it's clearly a lot of very subtle aspects to this. So thanks.
Yeah.
I had a follow-up question to one of the last comments you made at the end of your talk about this resampling map. So I had asked during the talk, like, what are the properties of this sampling map? And I think you even talked about this. Is what you were saying another way of saying is you don't yet have the abstract axioms that characterize the resampling map in some Markov category? That's what one of the main issues is?
Exactly. I mean, we have some abstract axioms that, well, I wouldn't say not for characterizing it, but at least for sort of saying that the properties that we would expect it to have.
Okay.
But at the moment, I'm not really sure how useful those are, because we still can't prove the law of large numbers from them, or at least it seems kind of, again, sort of circular in that one of the conditions again somehow. Whenever you try to prove it in a particular category, somehow you end up using the law of large numbers again, and then that somehow creates some circularity. But yeah, so what I'm trying to get at is that we have some abstract axioms for what it should satisfy, but it doesn't really seem satisfactory yet. But what we definitely don't have is anything like a general construction that would apply in a suitable range of categories or something. Although that would obviously be the best thing to have. Another subtle aspect to this is that this map, so it's well defined, and for any x, for any object x in Borel stock, and it goes from x to the n to n. From x to the n to x, that there's no way to make this, seems to be no way to make it natural. And that is really very strange somehow. Not even sort of laxly natural in the sense of, and it's a partial morphism to begin with, and so maybe one would expect here is only to sort of the equality to hold on the common domain or something, but even this seems to be problematic.
I just want to double check. Is Borel stock, is that a Kleisli category? And is the monad the Geary monad, or is that something else?
That's exactly right. Yes, it's the Kleisli category of the Geary monad on this category of standard Borel spaces and measurable maps. Yeah.
Okay, thanks. Oh, also, since you mentioned that, what seems to be the issue for making that morphism natural in the object?
Yeah. So One issue is that, let me actually draw the diagram again. So one sort of, let's say, still relatively simple reason for why it can't be exactly natural is because suppose that we start with a sequence in here where the relative frequencies, so where the limits do not all exist. The limits and the definition of it, where do I have it? Oh yeah, it's right here on top, yeah. So suppose that we start with a sequence where the limits don't all exist. And now suppose that we apply we have some measurable function, even f here, apply this to every element in the sequence, and then it may well happen that we get a sequence in y to the n where all where all these limits do exist. So then certainly it can't be exactly natural, but the most that we can hope for is a sort of lax naturality like this, that that when you look at the upper right composition, that whenever this is defined, then also the lower left composition is defined and results in the same, ends up doing the same thing. But even this turns out to be too strong, and the reasons for this are more subtle, and I don't think I can do them justice here right now. In particular, also because I don't understand them myself as well as I'd like to. But roughly, it has to do with, again, the Glivenko-Cantelli theorem, and things that actually come up in statistical learning theory and sort of for this theory behind machine learning. And for what sort of sets can you actually expect, which sort of sets can you expect to be able to distinguish from a sufficient amount of data? Sorry, if this is not helpful, I don't know how else to say it at the moment. But it has to do with things like this Vapnik-Chervonenkis theory and statistical learning theory, and so things like that.
Okay, thanks.
I had a question. Maybe someone was about to ask, but so there's some sense that like these Fs, I could imagine them happening in time or something. If you go back to your main slide, like it shows that you can't think of it that way, or at least if I'm understanding right, like you can't just say that these are kind of time goes up and I start with some things and I flip a coin and I actually get an answer, because the thing on the left has like kind of a different, they kind of come out at, the answer to the first F on the right is coming out at the second spot on the left.
Yeah, right.
So it's not really, you can't think in time at all. And I just was wondering, like, I don't know, what is that? Why does it, like when a computer scientist, I don't really know anything about probabilistic programming, but I imagine they actually produce results along the way sometimes. And so like, you wouldn't expect this thing to be true there, I guess.
Well, but I mean, all these Fs sort of happen in parallel, no? These are...
I guess that's true.
So yes. These are not temporally ordered to begin with.
That's right, but the one that's coming, that's true. But the one that's on the left is, if we call it X1.
Right, yes. This
one, we could also drop the second marginal on the left. And I guess the statement is still going to be true, right?
Yes, sure.
And then that way,
yeah.
things look a little bit better. So they keep the main property, but don't have this problem.
That's true.
That's a good point.
But it still works. The axiom still holds. I mean, I don't know. Yeah. The fact that you would even think it was okay without that means that we're not, like, I'm probably not thinking right about these being kind of like actually flipped coins or something.
Right. Well,
like not actually the same F or something. I think I'm just being very naive about how I'm reading it.
They're copies of the same coin. You clone the coin, you make a lot of clones of the coin, and then you can throw them all together.
Right.
But the important thing is that they're clones of the same coin. So usually you can't do that, and so you have to reuse the coin.
Yeah. Yeah.
Yes, I mean, thanks. Yeah, no, actually, I understand the question. Yeah.
Okay.
Okay. Does anybody else have any questions or comments? If not, I will end the live stream.
I have a quick question if nobody has a question, but not only if you can give a short answer. Can you say a little bit more about this uniform existence of limits, or is it going to take too long?
Sure. Yes. No. I can say a little bit about that. So, essentially, what makes it work in the particular case where, I mean, the most complicated sort of standard Borel space is the unit interval. So we only need to consider this case. And the definition that turns out to work is that we consider this, well, we take this definition whenever, but not for all S, but only for all S like this. So this basically means that we're defining the resulting probability measure on X in terms of its CDF. And then for all S of this form, then here imposing uniform convergence does the trick. So this means that resamp is defined for a given sequence whenever the thing on the right exists for all S of this form, and the limit exists uniformly in A. This is what turns out to make it work, because then we can basically don't even need to look at any other S because we have the CDF.
Nice. Thank you.
Okay. So thank you again, Tobias. Virtual applause. I will end the live stream now, but we'll keep this room open if anyone wants to hang around for any discussion or anything. So thank you.
Yeah, thanks a lot also for all the questions and yeah, listening so closely.